Hello, happy Autism Awareness Day, solid for the spectrum, and welcome to Physics Studio. It seems as though a number of you are still struggling with right-hand rule number 3, and so I wanted to pick that up by way of a question that someone asked yesterday. Now keep in mind, we have an assessment coming up at the end of the week after break, and you're going to have to cover in that everything from the basics of magnetism, the fields, the attracting, the repelling, to what's happening at the atomic level, right? How some atoms are themselves little magnets and how it has to do with the electrons and in the outer shells, all the way up to the motor and the generator. And what this question does is it puts a number of these things together. And so let's go over and take a look at this. Now, the question basically was, and it was from someone in period 12, I understand how to use the right-hand rule. I get it. I can manipulate my fingers and turn things over and get the correct answer. But what exactly is happening physically between the field, the current, and the forces? And that's a good question. And it's the basis of the chapter, but it's not at all obvious. So let's take a look at that. Now, for right-hand rule number 3, first thing we need is an external magnetic field, right? Right-hand rule number 1 is about a current carrying wire and how there's a field around it, right? But that's its own field. For right-hand rule number 3, we need a field imposed by something else, external. And so here in academic physics, because we don't have calculus, we have to keep things uniform. And so what we posit for the field is, if we have these two magnets, right, they each have their field going, and you know that there's that weird spider-like shape around them. But as we bring them together, right, they're going to eventually attract, which means we have a north pole and a south pole. If we bring these together but hold them apart a bit like that, between these two, you're going to get a pretty uniform field going from one to the other, like that. That's the kind of field we talk about when we use right-hand rule number 3. 6 ways to do that. Let's say right-hand rule number 3. So we need the external magnetic field, right? We can do that like this. Say we have a north and a south pole. And of course, in principle, this goes off, is itself a bar magnet. It goes off like this, and then has its own north pole. But the interaction between these two is much stronger, so we can ignore that. Now, we could also take these two magnets and swap them so that we had a south pole and a north pole like this. In this case, our field would be like that. And that's the B in right-hand rule number 3, where force equals B times current times length times sine of theta. And we'll just assume theta is 90 degrees for these so that we get the full effect. Now down here, same configuration, but now the field's going this way. So when you're asked to draw the external magnetic field in a problem like this, you're being asked to draw that. We're going to call that B. We could also configure it like this, right? North and south. In this case, the external field would be going like this. Right? And we would label that B so we know what these arrows mean. Now, we could, of course, swap north and south, and then the field would be going vertically up, right? Now, there's a 5th and a 6th possibility, which is that the field is going into and out of the page. And so, for into the page, right, this is a uniform field. We're going to draw it like this. then we would label that B, and that's our external magnetic field. Now, we could also have the field coming out of the page, in which case we'd go like this. And we call that B. And you can get more than one field in a problem, so let's call this field 1, field 2, field 5, and field 6, just to keep them straight. Now, for right-hand rule number 3, the next thing we need after we have that external field established is a wire. And it's going to be a copper wire like this, right? Something like that. Let's say we lay that wire in the field. And I'm going to give this field a little bit more so we can make it look symmetrical. We're going to lay that wire in the field like that. Copper wire, right? And that wire is just going to sit there because there's no net force on it. Now we know that because this is copper, each individual atom is itself a little magnet because of the unpaired electrons whizzing around in it. Do you remember all that? And so there are zillions of tiny little magnets in this copper wire, each one of which is experiencing a force from that field. But because copper is not ferromagnetic, all those individual little tiny atomic magnets are oriented randomly, and the net force on that wire with no current is 0. Now let's say though that we attach a power source and suddenly we have a current going that way. Now what that power source has done by imposing a potential difference is it's organized the movement so that the positive charge goes this way, though it's not really moving mathematically, it's the same, and the electrons flow that way. It's organized the movement of the charged particles in the wire. And what happens then is you get that organized magnetic field. And if we wanted to, we could do right-hand rule number 1 and find that the field loops like that. But once you've organized that, this wire becomes itself a magnetic object, just like a bar magnet or a compass. And when you put that magnetic object into a field, a magnetic field, it will experience a force. Right-hand rule tells you the direction. So if we put our, using the book's version, if we put our fingers in the direction of the current and we wrap our fingers toward the field, thumb gives the force. And we're going to put that force in the center here, though it's really acting all along the length of the bar. Using the other version, we would put our fingers in the direction of the field, thumb in the direction of the current, force comes out the palm, and we get the same thing. But that's the point. As soon as you run current through this thing, it becomes itself a magnetic object and it experiences a force. Now we found that these 3 quantities, the magnetic field, the current, and the force, are at exactly 90 degrees to each other. I mean, you can orient the current less than 90 degrees, it'll just lessen the force because of the angle theta. But we found that that force is always at exactly 90 degrees to both of those. That was a surprise. It didn't have to be that way, but that's the way the world is. Now let's say we run another conducting wire through this one, right? Just like that. And we'll give that a plus here, minus here, so that the current is going that way. Okay, now see, I've specified the field direction, the current direction. Now we need the force. Applying our right-hand rules, fingers in the direction of the current, wrap toward the field, thumb indicates the direction of the force. So the force is going to be that way. Using the other version, your skill sheet and the one that I prefer, fingers go in the direction of the field, thumb in the direction of the current, force comes out your palm and you get the same thing. Okay? So that is what the relation is between the field, the current, and the force. The current turns the wire into a magnetic object, The field exerts a force on it. The right-hand rule tells us the direction. Clear as a bell? Okay, so let's get started on the review. Good luck with that. And I'm thinking that we'll hold a Zoom, not today, but the following day, starting Tuesday and Wednesday of the week after we return. We'll have a Zoom conference at the beginning of class so that you can ask questions. So anyway, good luck with your review. Remember, post twice to the discussion board, and I'll talk to you later. See ya.